I'm going to discuss some exercises which use the techniques we have discussed from chapter 7 and 8. Remember that when doing these problems, you don't necessarily have to solve the problem in the same way I do. From 7 and 8, we learned several different methods, and you could apply maybe not all of those, but more than one on each of these problems, and so keep that in mind. The first exercise we'll look at. Here we're asked to find an equation of a quadratic which goes through the three given points. So these would be three ordered pairs. 1 would be the x-coordinate, and 3 would be the y-coordinate for an ordered pair. I want you to recall that the graph of a quadratic equation is a parabola. So we want to find a parabola which goes through these three ordered pairs. You could even sketch that out to kind of get a feel for what we're looking for. Just a simple sketch might tell you, because of the curvature, might tell you immediately whether we want a positive coefficient, a negative coefficient. So because we could be kind of overwhelmed with ideas right now, let's start from the beginning and think about, well, what does a quadratic equation look like? And you could actually have different answers. What I have here is that a quadratic equation has the form y equals ax squared plus bx plus c, and you might recall that from any algebra class. Now, because we know the equation of a quadratic, and this is a quadratic, a, b, and c would be constants here, and x and y, x is my independent variable, y is my dependent variable. So because I have this equation, we could actually use our ordered points to give us some information. Because 1 is x, and when substituted for x, when x is equal to 1, then we know that y is equal to 3. We can actually put that together, and we gain three different equations here. So for a y value of 3, I have plugged in x is equal to 1, 3 is equal to the sum of those three constants. 2, the y value from the second ordered pair, x squared would be 4, bx would be 2b plus c, and then the third one, negative 3 is equal to 9a plus 3b plus c. And take a minute and make sure it's clear where I got those from. Once you understand where I gained those three equations from, then when we look at this, this is actually a system of equations. Our unknowns are not x and y right now. Our unknowns are the coefficients a, b, and c. We have three equations and three unknowns. So this is a 3 by 3 system. You could do this solve this algebraically, and I recommend that's great if you want to go for that and try for that. To do this algebraically, you would maybe consider two equations. So pair two equations at once, so maybe the first and second, and maybe the first and third, and isolate, so maybe cancel c in both of those. Once you take the 3 by 3 and you can reduce that to two 2 by 2s in terms of two equations in terms of the same variables, that gives you a 2 by 2 which you can then solve using one of the techniques, one of the 5 techniques we've talked about before. I also understand that you might not want to use a whole half piece of paper to do this algebraically. So I remind you, matrix equations and solving systems of equations that are large using matrices, that is quite helpful. So you might need to use technology to do this if you don't know how to take inverses of 3 by 3s by hand, for instance. But fortunately, technology actually makes this a pretty fast problem. So what we're going to do is write this as a matrix equation, as you see here. On the right side, because of my constants a, b, and c already ordered, I've simply written the coefficient matrix times that column, and 3, 2, negative 3 would be my constants from the left. To solve this system, you'll recall, if we need to get a, b, or c, we need to cancel this coefficient matrix. So if I call this matrix, say, a or m, I want to multiply both sides by that inverse. I need to find the inverse of this. Fortunately, using technology, I can put this into a calculator. I have the inverse of that matrix, the 3 by 3, times 3 to negative 3, the column matrix, and that will give me a, b, or c. If you go ahead and type this into your TI-83 or TI-84, or an online calculator you might be using, you should find that a is equal to negative 2, b is equal to 5, and c is equal to 0. Here I've gone ahead and I've graphed that quadratic. What this is telling us is because our original equation had the form ax squared plus bx plus c, I've substituted negative 2 for a, 5 for B, and C would be 0. You will see here, after I graph this in Desmos, you can see that it does cross through those 3 points that we started with. So this would be our first example. Here you had a 3 by 3 system from the given information. Now it didn't immediately jump out at us, so we had to put some of those ideas together, different ideas that we have developed through this algebraic course. But putting all of that together, this really didn't turn out to be that difficult of a problem since we used matrices. If you did want to do this by hand, you can certainly do that as well. It would take you a little bit longer, and for now I'm just asking that you practice these techniques using technology. For exercise 2, in this problem we are finding the equation of a circle that passes through the points. Now if you'd like to pause the video and try this one on your own, go for it. Here, what I'm going to remind you of, first we need the equation of the circle. You'll recall that the equation of a circle has this form. H and K here were the center of the circle, and R was the radius of the circle. Now you will notice that this will give us a different system. This system may be nonlinear, and what I mean by that, once I use this equation, plugging in 0 for x, 0 for y, I'm able to gain some equations. 0 for x and 0 for y give me this equation, so this is what remains. Keep in mind, because this is a negative h, but that's all squared, I'll just have a positive h squared. The negative will make no difference. Anything squared will be positive. From the second equation, y was 6, so you'll notice what I did for this second equation is I went ahead and expanded that. Here I did have an x and a y that remained, and so I went ahead and expanded that to get this equation. Now, what is extremely different in this problem than the previous one is that this is a nonlinear system. So you'll notice from the first equation I have h, k, and r, so 3 variables. From the second equation, h, k, and r. Here k is linear, everywhere else it's squared. H, k, and r, so I have 3 unknowns and 3 equations. This is again a 3 by 3 system, but because some of the variables are squared, this is non-linear. It would only be a linear system if all variables were to the first degree. A nonlinear system, you should not try to apply matrices. So we need to do some, you should not apply matrices in the beginning, and I talked about that in a previous video. That doesn't mean you couldn't ever, but right now we are not able to. So we need to use some algebraic techniques to simplify this. Notice that when I put all the squared terms on the left-hand side, then the first one becomes h squared plus k squared minus r squared. The second becomes h squared plus k squared minus r squared is equal to, and here is what remains, etc. Now these are all quite similar, so I could actually use the transitive property. What I mean by that is if this sum and difference of these terms is equal to 0, but it's also equal to negative 36 plus 12k, as well as this third line, then that means those 3 are equivalent. Now that benefits us because if we set 0 equal to negative 36 plus 12k, well, that immediately tells us that k must be equal to 3. Furthermore, if we set 0 equal to that last line and substitute 3 for k, so if 3 is equal to k, this becomes 18 minus 18, so that 6h must be 0. And pause the video to make sure that algebra makes sense. What I'm doing is setting 0 equal to this expression, solving for k, plugging that in, and solving for what h must be if this term is also 0. Now that we know k is equal to 3 and h is equal to 0, substitute that into the very first equation. H will vanish. K squared will be 9, so I'll have 9 minus r squared is equal to 0. Therefore, r must be equal to 3. We started with a 3 by 3 system, 3 equations and 3 unknowns. We have now solved for each of those unknowns. K must be 3, h must be 0, r must be equal to 3. Those unknowns are the constants we need to write the equation of a circle. So again, recall the equation of a circle has this form. X and y will be the ordered pairs, so for any point on the circle, it should have the form x comma y. They need to remain as our variables since we want to solve for all points on that circle. So our final equation, notice that it is in terms of x and y, has the form x squared plus y minus 3 quantity squared is equal to 9. If if you graph this circle, you'll notice that it does go through those 3 ordered pairs. So this was our second example. In this example, we could not apply matrices because it was non-linear. The next example, we are asked to decompose the rational expression into the sum of terms with linear denominators. If you haven't seen this before, I'm going to try to talk you through what I mean by that. So here I started with a rational expression. You might recall these from earlier in the semester. First of all, with this rational expression, notice that you can factor the denominator, x squared minus x minus 6. It simply factors into the product of x minus 3 times x plus 2. Those are both linear factors. I took a quadratic and factored it into 2 linear factors, prime factors, in fact. When the instructions here say to decompose, what we want to do is rip apart this rational expression so that we have the sum of 2 new fractions, new rational expressions, with linear prime denominators. So notice that I want to find an a over x minus 3, the first factor, and a b over x plus 2. Now I don't know what these a or b need to be. However, if I were to work backwards, then notice if we were working backwards, to add 2 fractions, I would get common denominators. So I would multiply a by x plus 2 and b by x minus 3, as you see here, over the product of those prime denominators. This sum, so I don't know what a and b need to be, but I know that this must be equivalent to what I started with if this is even possible. So by assuming that this is what I need, so for some a or b, I know that this must be the same as what I started with, then that actually gives us a system of equations. So here's what I'm saying by that. Because we know that these 2 expressions must be identical, then that tells me the numerators must be the same, since they're denominators. If you ever have fractions with the same denominators equal to each other, then their numerators must be the same. Therefore, the numerator from the left must be equal to the numerator from the right. When I factor on the left, I notice that I have the sum of a plus b times x plus some constants, so no x's there, and that must be equal to x, 1x plus 1. That actually gives me 2 equations then. Because there are a plus b x's on the left and 1x on the right, that tells me that a plus b must equal 1. Equality means that both sides are equivalent, and if this is true, it must be true for all x's. So no matter what x I plug in, this will be an identity statement. That means that there must be the same number of x's on the right as there are on the left, and that's why I get this equation. I notice another equation. The constants on the left must be equal to constants on the right. Therefore, 2b minus 3b must be equal to 1. Well, if you'll notice, this isn't in terms of x's and y's anymore. However, we have a system of equations. This is a 2 by 2 system. My unknowns are a and b, and I have 2 equations. You can use any of the 5 or 6 methods that I've discussed at this point in the class. What I've talked through here is using elimination by addition. So if you take 3 times the first equation, you would have 3a plus 3b equals 3. The benefit of that is you could add the 2 equations now. 3a plus 3b equals 3. Summing that with the second one gives us that 5b must equal 4. You'll have 3 plus 1, which is where your 4 comes from. Here I'd have a 3a plus this is an a, and I just now noticed that that was wrong. So this should be 2a minus 3b. This allows me to solve for b, so b must be equal to 4/5. By working backwards, since a plus b equals 1, a must be equal to 1/5. Therefore, this first rational expression breaks up into the sum of these final 2 fractions. Fourth problem, I'm going to solve a linear programming problem. These are called linear programming problems in mathematics because they are dealing with an objective function, often a linear equation, but not necessarily, it could be nonlinear. And you are given constraints that are here given to us in linear equations, so linear inequalities. Now, in a word problem, you might have to determine what your objective function and what your constraints are. So this one is not presented to you as a word problem, but it does help you understand how to relate the ideas if you do encounter a word problem. Sometimes it can be overwhelming when you're given all these equations and all this math jargon and you're not sure what to do with it. But just take things one at a time. These are a set of inequalities, and so here I know X, maybe number of something sold, number of t-shirts sold. X must be positive, Y must be positive, maybe Y is the number of pants a business sells. And I need to keep, maybe this is production constraints. These are production constraints, or maybe workers, the number of hours they're hired. Maybe these are constraints for how many I can produce. So when given all of this information, it might be a good idea to graph this. Now, fortunately, Desmos makes this quite easy for you all to graph. You'll notice that I have X and Y are greater than or equal to 0. So I've graphed that. We're in the first quadrant. X plus 2y is less than or equal to 150, and 5x plus 2y is less than or equal to 350. Now, normally you would need to solve for the intersection points of all of these. So you'll see I have two lines here, excluding the axes, and they intersect. I have 1, 2, 3, 4 intersection points because I had 4 equations. So I actually get this quadrilateral where every single equation is shadowed. So this space right here is a quadrilateral that I want to focus on. These corner points, 1, 2, 3, 4, and I'll have 4 corner points for quadrilateral, give me the optimal values for X and Y that I should examine for my objective function. When identified, so identify these X and Y coordinates, and it may be difficult to see on my picture here, but remember in Desmos you can actually just click on these to find them. Normally, if we were doing in this in class, we would do a little bit of practice on how to do that algebraically. Remember, you could use any of your methods. So here, if I know that X is equal to 0, I might plug that into these inequalities to solve for their Y values, and I would get a Y value from this one of 750, because this graph is that line right there, or the graph of this line is demonstrated, is drawn here. This line is given here. The x-intercept, so the other one, this is the y-intercept. If y is equal to 0, you can plug that in here. And when y is equal to 0, it looks like we get 700. 5x equals 3,500, so x is equal to 700. So x is equal to 700. So that would be this x-intercept here. The other point would be the intersection of these two lines. If you took maybe the 4th equation minus the 3rd equation, it would give you 4x is equal to 2,000, and you would get x is equal to 500. Substitute that back in to get y is equal to 500. So these are the 4 points. Once you've identified those 4 ordered pairs, if you had more constraints, you might have more ordered pairs, then you will substitute those into your objective function. Now, your objective function does not need to be graphed. Your objective function is what you are looking to maximize or minimize. Perhaps for business it would be profits. So once you find your x and y, plug those into your objective function. Here I get z is equal to 0, or these values. And then identify the largest and smallest value for z. Well, of course, z equals 0 will definitely be the minimum out of these, and z equals 60,000 will certainly be the max. This tells us that the maximum of our objective function occurs when we have 500x and 500y. If this z were the profit of a company and x were the number of t-shirts sold and y were the number of pants, then we want to get close to or exactly 500 for each of those items sold, so that we meet our maximum profits. And of course 0 would be our minimum, and so this would make sense, for example, for a profit function. So this is an example of a linear programming problem.